Ernest Rutherford, A Brief Biography. Ernest Rutherford was a New Zealand physicist who came to be regarded as the father of nuclear physics. He is often considered to be the greatest experimentalist since Michael Faraday and is credited to have discovered the concept of radioactive half-life, the radioactive element radon, and even differentiated and named alpha and beta radiation. For his work, he was awarded the Nobel Prize in Chemistry in 1908. Making him the first Ocean Nobel laureate. Ernest Rutherford was born on 30 August 1871 in Brightwater, in the colony of New Zealand, to James Rutherford and Martha Thompson. His father had emigrated to New Zealand from Scotland to raise flax, the common New Zealand perennial plants Phormium colensoi and Phormium tenax. His mother was a schoolteacher. Rutherford first began studying at Havelock School in the town of Havelock in the Marlborough region of New Zealand. He then enrolled at Nelson College, the oldest state secondary school in New Zealand, and went on to win a scholarship to study at Canterbury College under the University of New Zealand. In Christchurch, Rutherford frequently participated in the debating society of the college and played rugby. He went on to obtain his Bachelor of Art (BA), Master of Art (MA), and Bachelor of Science (BSc) degrees. He also invented a new form of radio receiver during his 2 years of research, for which he was awarded the 1851 Research Fellowship from the Royal Commission for the Exhibition of 1851. The fellowship gave him the opportunity to travel to England for his postgraduate studies at the Cavendish Laboratory, University of Cambridge, where he became one of the first researchers allowed to research at the university without a Cambridge degree under the guidance of British physicist J. Thomson. With Thomson's help, Rutherford went on to detect radio waves at half a mile, briefly holding the world record for the distance over which electromagnetic waves could be detected. Unfortunately, when he presented his results at the British Association meeting in 1896, he found out that he had been outdone by Italian inventor Guglielmo Marconi, who was also presenting his results at the same meeting. Upon arriving at Cambridge, Ernest Rutherford began working with J. Thomson on the conductive effects of X-rays on gases. Their research led to the discovery of the electron, which was presented to the world by Thomson in 1897. Rutherford was excited to hear about Henri Becquerel's experience with uranium, prompting him to begin exploring its radioactivity. His work led to him discovering two types that differed from X-rays in their penetrating power. In 1898, Ernest Rutherford, aged 27, was recommended by Thomson for a position at McGill University in Montreal, Canada, as a replacement for British physicist Hugh Longbourn Callender, who was going to Cambridge. Rutherford was accepted for the position, finally giving him the opportunity to marry his fiancée Mary Georgina Newton in 1900. A year later, the couple would go on to have a daughter named Eileen Mary. Rutherford continued his research on radioactivity in Canada. In 1899, he coined the terms alpha ray and beta ray in order to describe the two distinct types of radiation. He also discovered that thorium gave off a gas that produced an emanation that was in itself radioactive. Further into his research, he discovered the concept of radioactive half-life when he noticed that a sample of this radioactive material of any size invariably took the same amount of time for half the sample to decay. In 1900, while Ernest Rutherford was at McGill University, he was joined by a young chemist named Frederick Soddy, who would go on to win the Nobel Prize in Chemistry in 1921. Rutherford asked Soddy to identify thorium emanations. After Soddy had managed to eliminate all the normal chemical reactions, he suggested that it might be one of the inert gases, which they named thorin, later found to be an isotope of radon. Together they found another type of thorium that they called thorium X and even traces of helium. During the course of their research, which lasted until 1903, they worked with samples of radium from Marie Curie and uranium X from British chemist and physicist William Crookes. In 1903, after almost 3 years of research on radioactivity, Ernest Rutherford and Frederick Soddy published their findings, Law of Radioactive Change. Rutherford and Soddy showed that radioactivity involved the spontaneous disintegration of atoms into other matter, which was as yet unidentified. Until then, atoms were assumed to be the indestructible basis of all matter, and, therefore, the idea of the atoms of radioactive substances breaking up was a radical and revolutionary new idea. In 1900, French chemist Paul Villard discovered a type of radiation emanating from radium, but he did not care to name it. In 1903, Rutherford contemplated this radiation and came to the conclusion that it must represent something different from his own alpha and beta rays due to its greater penetrating power. Rutherford went on to name this radiation gamma ray. In 1904, Rutherford suggested that radioactivity could solve the long-standing question of explaining the existence of the Sun as a source of energy for millions of years during the painstakingly slow biological evolution on Earth proposed by biologists like Charles Darwin. In 1907, Ernest Rutherford returned to Britain to take the chair of physics at the Victoria University of Manchester. The same year, he and solar physicist Thomas Royds allowed alphas to penetrate a very thin window into an evacuated tube. As the alphas accumulated in the tube, the spectrum obtained from it changed. Eventually, the clear spectrum of helium gas appeared, showing that alphas were at least ionized helium atoms and probably helium nuclei. In 1908, Rutherford, aged 37, was awarded the Nobel Prize in Chemistry for his investigations into the disintegration of the elements and the chemistry of radioactive substances. Even though Ernest Rutherford had done some groundbreaking work to be awarded the Nobel Prize, his most well-known work was actually performed in 1909, a year after winning the prize. Rutherford, along with German physicist Johannes Geiger and English physicist Ernest Marsden, performed the Geiger-Marsden experiment, which demonstrated the nuclear nature of atoms by deflecting alpha particles passing through a thin gold foil. They then looked for alpha particles with very high deflection angles and found them, though they were rare. Such types of deflection angles were not expected from any theory of matter at that time. With the help of these results, Rutherford formulated the Rutherford model of the atom in 1911, suggesting that a very small charged nucleus containing much of the atom's mass was orbited by low-mass electrons. In 1919, Ernest Rutherford found that nitrogen and other light elements, when hit with alpha particles, ejected a proton, which he called a hydrogen atom. This showed him that hydrogen nuclei were a part of nitrogen nuclei, and he decided that a hydrogen nucleus was possibly a fundamental building block of all nuclei and even possibly a new fundamental particle as well, since nothing else was known from the nucleus that was lighter. In 1920, Rutherford, extending upon the work of German physicist Wilhelm Wien, postulated the hydrogen nucleus to be a new particle, which he called the proton. In 1921, while Ernest Rutherford worked alongside Danish physicist Niels Bohr, he theorized about the existence of neutrons which could somehow compensate for the repelling effect of the positive charges of protons by causing an attractive nuclear force, thereby keeping the nuclei from flying apart from the repulsion between protons. He suggested that the only alternative to neutrons was the existence of nuclear electrons which would balance out some of the proton charges in the nucleus. Another fact that gave his theory some credibility was that it was known at the time that nuclei had about twice the mass that could be accounted for if they were simply assembled from protons. However, it was yet unclear how these nuclear electrons could be trapped in the nucleus. In 1932, British physicist and Rutherford's associate, James Chadwick, would go on to prove Rutherford's theory of neutrons after recognizing them when they were produced by bombarding beryllium with alpha particles. In his later years, Ernest Rutherford became more of a mentor to other young scientists. After replacing J.J. Thomson as the Cavendish professor and director, Rutherford mentored future Nobel laureates such as Ernest Walton, John Cockcroft, Edward Appleton, James Chadwick, and Patrick Blackett. During the war, he was assigned to a top-secret project to solve practical problems of submarine detection by sonar. In 1925, Rutherford called upon the New Zealand government to support research and education, which eventually resulted in the foundation of the Department of Scientific and Industrial Research (DSIR) the following year. Rutherford even served as president of the Royal Society for 5 years between 1925 and 1930 and was also appointed president of the Academic Assistance Council. In 1933, he was awarded the inaugural T.K. Sidey Medal, set up by the Royal Society of New Zealand, for his outstanding scientific research. Shortly before his death, Ernest Rutherford suffered a small hernia which he neglected. The hernia became strangulated, resulting in him falling seriously ill. He immediately underwent an emergency operation in London but to no avail. 4 days after the operation, on the 19th of October 1937, Rutherford, aged 66, died of intestinal paralysis at Cambridge. He was cremated at Golden Green Crematorium, after which his ashes were moved to and buried in Westminster Abbey along with other great British scientists such as Charles Darwin and Isaac Newton. Ernest Rutherford is widely regarded as one of the greatest scientists in history. His own personal research work and work conducted under him as laboratory director established the nuclear structure of the atom and the essential nature of radioactive decay as a nuclear process. The work of Rutherford and his team was pioneering and groundbreaking. Blackett, while working under Rutherford, demonstrated induced nuclear transmutation by using natural alpha particles. His team also demonstrated artificially induced nuclear reactions and transmutation by using protons from an accelerator. 2 of his students, Cockcroft and Walton, succeeded in splitting lithium into alpha particles by bombarding it with protons from a particle accelerator they had constructed. Since his death, Rutherford has become one of the most important and influential figures in scientific history. Several institutions, awards, buildings, parks, streets, scientific discoveries, etc., have been named after him. Rutherford's work and achievements have rightly resulted in him being regarded as the father of nuclear physics.